Standard contents of a pre-calculus course. I've listed main topics in one color and some notes on each of those topics in another color. And a little note in red down here. Note in red says pre-calculus is a transition to calculus, and the goal is to make calculus as easy as possible and as powerful as possible. Now there are other goals for pre-calculus course not related to calculus. There's important content for people who aren't going to go beyond pre-calculus. A lot of valuable things in the course, but the course needs to be modeled around a transition to calculus. Okay, and the topics in a typical pre-calculus course include analytic geometry in the plane, functions and their properties, constructing graphs. Now I've editorialized a little bit here. I say functions and function families as entities. In a transition toward calculus, we need to understand the different types of elementary functions and the family of each of those functions. And we're not going to explain exactly what that means right now, but the functions and their families are mathematical entities and need to be understood as such. Okay? You need to be able to arrange expressions and equations in a form that fits a given purpose, whatever that purpose might be. Then we have trigonometric functions, triangle trigonometry, trigonometric identities, vectors, through dot products and projections, matrices, mostly centered around solutions of systems of equations, but getting into very basic matrix algebra with identities, inverse matrices, and so forth. Sequences and series, mostly in a context of identifying number patterns, classifying different kinds of number patterns, the notation of sequences and series, and summation of a sequence. Then we have applications and modeling, which will have a greater or lesser emphasis depending on the specific course. The idea of rate of change, which is essential. It's an essential idea. It's the fundamental idea of calculus, and solution of equations. Now these have been listed in no particular order, but these are the things that we study in pre-calculus, that are typically studied in pre-calculus. Within analytic geometry, we have the elementary analytic properties, the Pythagorean theorem, the distances between points, midpoints of a segment between points, circles, lines in the plane. And that's typically covered first semester. This is all pretty elementary, except that in studying circles, we do get into completing the square to determine exactly where the circle of a given quadratic form might lie and what its radius might be. In second semester, typically, we get into conic sections, parametric equations, and polar coordinates. Ideally, we get into these. These things often end up being glossed over. Not a very good thing. But one of my purposes here is to outline things that I think maybe need to be covered in a little more depth for students who are actually going to go into calculus, especially into a rigorous calculus course, and into fields that rely on calculus. Okay, functions and their properties. Our basic functions: linear functions, power functions, polynomial functions, rational, exponential, trigonometric, logarithmic, inverse functions, quadratic functions, which are really a special case of polynomial functions, but very important and deserve their own classification. So a subset of these forms the set of elementary functions in terms of which almost everybody does almost everything in mathematics. That's a bit of an overstatement because we don't use these functions a lot, say in linear algebra that comes out of matrices, but these are very fundamental, and we need to understand this classification of functions and how these functions are combined by sums, products, quotients, and composites. We need to understand how to construct graphs, not how to punch them into a graphing calculator. That's a 5th grade skill. Okay, we construct graphs, and this is a hard sell for students because of widespread misuse of calculators in the secondary curriculum. In Virginia, that's probably a direct result of the permissibility of calculators on the SOL test. I've mentioned functions and function families as entities. This should be pretty self-explanatory. We need to be flexible in the way an expression or equation is written down. There are many, many equivalent expressions, and it's very difficult to get really good at this. We don't really expect people to perform miracles with this, but we need to begin to understand what it means to arrange an expression or an equation in the form that fits our present purpose, whatever that purpose might be. Trigonometric functions, something that's very, very often glossed over in a pre-calculus sequence. Extremely important for moving on into calculus, and extremely important for applications. Trigonometric functions are generally defined in terms of the circular model for the sine and the cosine. And in terms of that circular model, we understand how graphs are constructed. Now, graphs are constructed by knowing graphs of very fundamental examples of various different types of functions, and by knowing how to transform a graph, how to transform a function by transforming a graph, how to transform a function into the desired form by using translations and stretches and compressions, okay? Horizontal and vertical translations, horizontal and vertical stretches or compressions of graphs, and that comes to maximum fruition with trigonometric functions for reasons that I won't go into right now, but extremely important and often undertaught. Triangle trigonometry, which is generally pretty well done. Trigonometric identities. The more abstract we can get with our applications here, the better, but we can cover the fundamentals and leave the deeper applications for later courses, just because of the reality of time and student willingness to work and student preparation. Vectors through dot products and projections, extremely important. Matrices, we mentioned, and matrix algebra, the various things that we can do with matrices, mostly applied to systems of linear equations, but also to the algebra of matrices, and the other topics that I mentioned. And let me give special mention to the idea of rates of change, difference quotient, rate of change, slope, interpretation of a difference quotient, interpretation then of a rate of change, interpretation of a slope. Completely fundamental for the transition to calculus. And solution of equations, and I mean solution of algebraic, logarithmic, exponential, trigonometric equations.